Entropy, a measure of the efficiency of an encoding. Recall that Claude Shannon's definition of information entropy resulted from his desire to find a way to efficiently send messages without losing any information. Although we will not need to encode and transmit messages electronically, a little understanding of encoding fundamentals will go a long way. For example 3 in the previous section, we calculated the entropy of the random variable x to be 1.5 bits. Having explored the idea of a non-whole number of bits before, we conclude that 1 bit is insufficient to uniquely encode the values of x, while 2 bits, in some sense, are more than what is actually needed, leading to wasted resources. Informally speaking, a good strategy for efficiently encoding the outcomes of a random variable consists of the following steps. Determine, if you can, the shortest bit strings needed to uniquely represent all of the outcomes of your random variable. 2. Inversely pair bit strings with outcomes. That is, assign the longest bit strings to the least probable outcomes, and the shortest bit strings to the most probable outcomes. Let's apply this strategy to the random variable x in example 3. 1. Any 3 of the 4 2-bit strings 00, 01, 10, and 11 could be used to uniquely represent the 3 outcomes red, clubs, and spades. But can we judiciously choose just 2 of them together with a single digit? Yes, consider the 2-bit strings 10 and 11 along with the individual digit 0. These can be used to uniquely represent 3 distinct outcomes without leading to ambiguity when these strings are concatenated in various combinations, which would represent a sequence of successive card selections. Whereas 10 and 11 together with the single digit 1 would not work, since these assignments lead to ambiguous sequences of zeros and ones, such as 1110, which could be interpreted as either 1, 11, 10, or 11, 1, 10. Can you find another trio that would work as well as 10, 11, and 0? 2. We pair the shortest bit string 0 with the most probable outcome, namely red. Each bit string 10 and 11 can be paired with either clubs or spades, since these bit strings have the same length and the outcomes clubs and spades are equally probable. Because these last 2 assignments are arbitrary, we will pair 10 with clubs and 11 with spades. Therefore, the average number of bits per value of x for the above encoding is 1 bit times 0.5 plus 2 bits times 0.25 plus 2 bits times 0.25, which is equal to 1.5 bits. Observe that we were able to achieve the minimum number of bits set by the entropy of the value of x, which is 1.5 bits. But if we had been careless in our encoding, this might not have been the case. For instance, if we had assigned the bit string 0 to clubs and the bit string 10 to red, then the average number of bits per value of x would have been 1 bit times 0.25 plus 2 bits times 0.5 plus 2 bits times 0.25, which gives 1.75 bits. If we had to transmit on average more than 1.5 bits per value of x because of a poorly designed encoding, then we would not be making the most efficient use of our resources. On the other hand, an inadequate encoding that results in transmitting, on average, fewer than 1.5 bits, then we would not be sending enough information to resolve the uncertainty about the specific values of x that we want to convey. In other words, the entropy of the random variable x is a lower bound on the average number of bits per value of x we need to transmit. Using less than this number would not be good if the goal is to unambiguously describe the sequence of values of x we want to transmit. In other words, our encoding scheme would have fallen short of accomplishing what we set out to do. The following diagram summarizes the three situations. Technical note: although it may not be possible to encode a random variable x in a way that immediately achieves the lower bound set by its entropy, it has been proven that there will always be an encoding, such as a Huffman encoding, whose average length approaches h of x as the average block size goes to infinity.